In this video, we'll start discussing vector fields, which have many applications, and they appear whenever you assign vectors to points in space. So examples from physics would be the gravitational force is a vector field, because to each point in space we can assign the vector of the gravitational force that acts on a body that is put in that point or placed in that point. Electric fields are also vector fields, and so are wind maps. So if you look at a map, and for each point, each location, to each location you assign the velocity vector of wind at that point, you get a vector field. The example I'm showing you, of course, is changing in time, so it is a vector field that depends on time. For us, a vector field will be a static object, so you have to imagine each frame in this movie being a vector field. So let me start with the definition of vector fields, which can be defined both in 2 and 3 dimensions. So I'll start with the 2D definition. A vector field on R2 is a function which we'll denote by capital F, and we put this arrow notation on top of it, so we remember that it takes vectors as values. So what it does, it takes points from a region of R2 of the two-dimensional plane, and it assigns 2D vectors to each point. So you take an input point with coordinates x and y, and the output will be a 2-component vector f of x and y. So it has 2 components, which I'll denote with capital P and capital Q. So P depends on x and y, and it is the first component of our vector, and Q also can depend on x and y, and it's the second component of our vector, which is expressed in terms in the standard basis ij. So this is a vector field on R2. This is how a vector field on R2 is defined, and similarly you can define vector fields on R3, where you take points in 3D space with coordinates x, y, and z, and assign to them vectors, 3-dimensional vectors with components p, q, and r, let's say. So this is also an example of a vector field on R2, and I'll give you its formula. So f of x and y will have components minus y and x. Okay, so if you assign to the point with coordinates x and y the vector minus y I plus x j, you will get this vector field. We need, well, let me ask you a question perhaps at this point. So let's consider a different, slightly modified version of this vector field that I've just showed you, where instead of minus y and x, we have minus y over the square root of x squared plus y squared times I, plus x over the square root of x squared plus y squared times j. And my question is, what happens to the vectors in this vector field as we move away from the origin? Will these vectors get longer, shorter, or will they stay the same, of the same length? So pause the video and select your answer below. Okay, I hope you paused it and realized that if you look at the length of any vector f of x and y in this vector field, you have to take the square root of the squared sum of its components. So we are squaring minus y over root x squared plus y squared and x over root x squared plus y squared, and we add these up. If we do that, we get, well, y squared over x squared plus y squared plus x squared over x squared plus y squared under the square root. But if you look carefully, this is just x squared plus y squared over x squared plus y squared, so that's just 1. So indeed, at every point in the plane, we assign a vector that is a unit vector. Okay, so it was the third option that was correct. Okay, a few more definitions before we end this video is an important definition is a gradient field. So if you have a function of two variables, you can make a vector field out of it if you take its gradient, and that is something we've seen before. The gradient vector of a function may be defined in a region of R2, maybe in the entire plane R2. So f is a function and its gradient field is the vector field that you obtain by taking its gradient vector at each point in the domain of f. So its gradient field, capital F of xy, is just the gradient of f at xy. Okay. So we can assign make vector fields from functions. Now the reverse process cannot always be done. So it's not always true that a vector field arises as the gradient field of a function. If that happens, we talk about, then it's a special type of vector field which we'll call conservative. So the vector field f is called a conservative vector field if there is a function f such that f arises as its gradient field. Capital F arises as the gradient field of little f. Okay? So this is an important concept. Conservative vector fields are all over physics, so we will see more of those in later videos. Okay, I hope you enjoyed this video, and I'll see you in the next one.